a minute, sir.
Okay. Okay. Go.
Okay, sir, start. Good afternoon, all of you. Our second phase of FDP optimization is on VLSI implementations of convolutions by Professor Dr. Rajesh Bhatija sir from SDIT Dosa. Now I invite you, sir, for the speech, please.
Thank you, Dr. Mulchan sir. Uh, it's a great pleasure to among the your learned faculties members so that I can share my knowledge to you. Uh,
Okay, sir.
uh, this Vedic convolution, I must say, is the I had built this during my PhD, and the the idea behind the Vedic convolution is like that there are linear convolution, there is circular convolution, but if we take the linear convolution, uh, then there is a problem which is occurring that is called linear shift. So there can be changes we can do on the linear convolution. Is that visible? First of all, tell me. Is that visible? What I am writing, is that visible to all?
No, sir. It is not in frame.
Okay. So, okay, it is not in place. Now, now,
Is it? It's okay now, sir. It's okay.
okay. So, in okay, okay, okay. So, the convolution is a basic process in the LTI system, that is the linear time invariant systems. A system is called linear as well as time invariant system when you provide a system input x1n and you get output as y1n, and at the other time if you put x2n and you will get y2n. Now at the third time to the same system as, if I write a1 x1 n minus n naught plus a2 x2 n minus n naught, and it results in a1 y1 n minus n naught plus a2 y2 n minus n naught, then we call this system as linear as well as time invariant system. Now, in the LTI system, there is the process which is called convolution. In this convolution process, if I put xn as an input, I will get output as yn. This is the, excuse me, this is the standard symbols we use for a LTI system. And a LTI system is characterized by its impulse response, and that impulse response is denoted by Hn, right? I'm considering a discrete time system. That's why I'm using all n here. and this n should be integer for simplification and for easiness of the calculation. We can use also the continuous time system. In that case, we can write xt, it will be yt is the output, and ht will be the impulse response, right? Now, if we provide del n, that is the impulse signal, unit impulse signal in discrete time, which is a sample at n equal to 0 and elsewhere it is 0. Now, if we put this signal to the LTI system, then the output is the HN, right? Now, if I shift this by a small amount, that is time shifting, if I put in the input, then what this system is time invariant. So in that case, the output must be Hn minus N naught. If now I multiply a send Xn naught to this system, then it will be Xn naught into H of n minus N naught. Why? It is following the homogeneity property, and homogeneity property is the basic property or one of the essential property of the linear system. And if I now vary this n naught from minus infinite to infinite, and then give these inputs, these will be the input, for example, x of 1 into del of n minus 1, x of 2 into del of n minus 2, x of 3 into del of n minus 3, and so on. That is, if I vary this n naught from minus infinite to infinite, I sum it out. So it will be, look, I can write it like this, n naught equal to minus infinite to infinite here. And here, because this system is a linear system, it follows the superposition also. So the superposition property tells us that a1 x1n plus a2 x2n is their input, then output will be a1 y1n plus a2 y2n. Now, if I have here the output has the output will be n naught equal to minus infinite to infinite x of n naught h of n minus n naught, right? Now, in place of n naught, I can write it x of r or any other variable I can choose, right? So suppose example, if I use x of n and here h of r minus n, and n equal to minus infinite to infinite, right? So we can put it like this. And what is this? This is nothing but yn, right? Because we are giving the input, whatever the input we are giving, the output will be same over here, right? Now, what is this signal? What is this signal? Let me take a fresh page. So this will be summation n equal to minus infinite to infinite x of n into del of n minus r. Or we can take n minus n naught, right? Now, this pairing, right? Or n naught we can write here, there is no problem, no issue over here. Now, what is the value of this? This is a product of a impulse function at particular point n naught and this n naught is varying from minus infinite to plus infinite, right? This n naught is varying from minus infinite to plus infinite, right? And there is a property of impulse function that is called replica, uh, that is called shifting property. Shifting property is x of n naught into del of n minus n naught will be equal to x of n into del of n minus n naught will be equal to x of n into del of n minus n naught, right? Uh, I hope you are getting this property very clear, and I know all the faculties are there. So this is very basic property, shifting property. Now, if I write in place of this value over here, it will be summation n equal to minus infinite to infinite x of n del of n minus n naught. And in that case, this x of n we can take outside of this summation and not equal to minus infinite to infinite, right? Now, what is this value? This value is nothing but 1. Why this is 1? Because we are shifting the del n from a point 0 to minus infinite and plus infinite. So it will look like this signal, right? And all the values are 1. So if I take this, it will be 1, then 1, and then all are 1. And then when we are multiplying over here, it will be simply x of n in the left hand side. And the right hand side will be nothing but y of n, right? So y of n will be given by n naught n equal to minus infinite to plus infinite. It will be x of n naught into h of n minus Am I audible to all? Pawan Sharma?
Yes, sir. Yes, sir.
Okay. So y of n equal to n naught equal to minus infinite to infinite x of n naught into h of n minus n naught, and this is called the convolution sum, right? So why I am trying to give this thing over here, because everybody should know the convolution is basically a process to calculate the output of an LTI system, right? So hope all of you know this, and I think it will be go to the more research oriented work. This is the very basic thing, and everyone should know this thing. Whoever is CSE and EE and EC branch, they must know all these things. Now we can go to the next part. Next part of the Vedic convolution is how we can achieve the fastness in the convolution operator. That is, fastness means how we can implement that, how we can make a chip of the Vedic convolution so that it gives the faster results as compared to the uh, conventional convolution method. Now, to show that, I'm using an example of 4-bit sample problem. Suppose x of n is 1, 2, 3, 4, and h of n is 2, 3, 4, 5. I'm taking four samples, so it doesn't mean that we can take only 4 or the same numbers. We can take any number over here in the linear convolution, but when we do the circular convolution, we have to take the same number of samples of x of n and h of n. Now, this 4 samples, if I giving, then the output sample must be 4 plus 4 minus 1. That is, the 7 samples should be there, right? And in the convolution, or rather we can say conventional method, I'm showing to you. In the normal conventional method, it will be 1, 2, 3, 4. We have to write it here, and 2, 3, 4, 5 we will write over here, right? This is called the matrix method to compute the convolution, right? Will be multiplied. So 4, 8, 12, 16, 5, 10, 15, and 20 will be there, right? And then we draw the diagonals like this. We draw the diagonals like this, right? And in individual diagonal, whatever is the value is there, we will write it over here. 2, 3 plus 4, 7, 4 plus 6, 10, plus 6, 16, 5 plus 8, 13, and 9 or 8, 17. So it will be 30, 10, and 24, so 34, 15, 16, so 31, and 20. So these will be the y of n value, that is the output value, right? This is explained, this matrix approach is explained in DSP Sullivan book, right? But in Sullivan book, it is not mentioned that if there is a sample value is over here at n equal to 0, and this is suppose here at n equal to 0, then where the n equal to 0 lie over here, it is not mentioned. So I had invented that thing, that where the n equal to 0 will be there, right? So n equal to 0, the method to find out at which is n equal to 0 in yn is as follows. So n equal to 0, here x of n is 2 values, so mark that as with a circle, and here mark this as a circle. This is h of n values, and this is x of n values, right? Now this 4 value and this 2 value, that is the circled values, are multiplied together and it is coming over here, right? And this diagonal sum is over here. 1, 2, 3, 4. So it is 4 over here. So this is n equal to 0. Right? You can check this is correct when you do with the other methods of the matrix. That is the K method is there also, right, of the convolution. And there are a lot of other conventional methods are there, right? This is one of the conventional method we have in the normal textbooks. In the Sullivan book, it is given. In Procase, it is given. But in these books, it is not mentioned that where the n equal to 0 lie. And that I found through my research, and it is coming over here like that thing. Right? Now, we go to the next point. That is this is the conventional method, that is the matrix method. And you can see in this conventional method, when we try to implement a chip on this basis, then definitely it requires lot of multipliers, lot of adders will be there, right? So if we build through the schematic editor, Tanner EDA tool schematic editor, which I show you in my yesterday lecture, that we can add the more number of multiplier, more number of adder, but the problem is this: multiplier take lot of time. If it is taking lot of time, then it is not a good processor, right? So we have to use minimum multipliers, as well as if I use the multiplier, it should be fast, right? So that I should get a fast output as compared to the other inputs, right? Now, my method, that is the Vedic convolution method, is as follows. In this Vedic convolution method, which I have invented, is like this. In this, I have used the UT Sutra. That is, I blend this UT Sutra in this Vedic convolution. The UT Sutra, we already discussed in the previous session of mine in the yesterday. I will not repeat it out over here. Now, if I have here the samples as 1, 2, 3, 4 and 2, 3, 4, 5, then what to do? Just a minute, right? Just is that visible now properly? Is that visible now properly? JP sir?
Yes, sir.
Jitendra Yadav sir?
Yes, sir.
Jitendra Yadav sir, is that visible?
Yes, sir.
Okay, okay. So my method of the Vedic convolution, I have used the UT Sutra or UT technique, rather UT technique, I must say. In this, what I have done, I have taken these two samples over here and these two samples over here. right? That is the LSB and MSB. And then the crosswise. Actually, UT Sutra is known as, the other name of it is crosswise multiplier. Right? So if you recall from the yesterday lecture, it is 1x1. Right? This is the pattern of the crosswise multiplier UT Sutra is. Now, LSB is 3, 4, 4, 5. Here we have put, here 1, 2, and 2, 3 we have done. Then here we write 1, 2 this value and 4, 5 this value. Here we write 3, 4 and 2, 3. Right? And then we take the VLSI, we are not doing the paralleling. Until and unless this 4, 6, 8 is drawn, then we cannot sum it out over here, right? But in this case, these are individual part, this is individual part, this is individual part, and this is also individual part. So we don't have to wait for this to compute and then we will compute this, right? Now this 4 and 5 and 3 and 4, what I have to do here, I have to use the again UT Sutra for this. The same thing, this is 1x1, right? So 4, 5 are 20, so 0 here and 2 will be the carry. This is the math. I hope it is visible. JP
Yes,
sir,
sir.
is this visible?
Yes, sir.
Okay. So this is the this is the conventional method, right? 13, 12, 14, 8, 9, 11, 12. These are the samples of 2 x of n. In place of x of n and h n, I have taken g n and f. There is no problem in this. And then we are having in the matrix method, we multiply 8 with this, with this, then this, and then this, and then it is shifted, and then it is diagonally added over here, right? So this is the direct method, and there is a drawback, you know. Now in my method, just see, is that visible? Is that visible? This portion is visible? JP sir?
No, sir.
JP sir? Is that visible? Not. Okay. Now, JP sir, is that visible?
No, sir.
No, sir.
No, sir. It is becoming blur, sir.
Just a minute.
Yes, sir. Now,
Is that
now it is visible, sir, and clear.
Clear, sir, clear. Okay.
okay? Is that visible now? Now?
Sir, it is looking like blur
Is that
type.
visible now? Mujal sir?
Visible, but
Visible, but sir, blurred, sir.
Okay, visible but blur. Now,
Not
Now?
clear, sir.
is this clear now?
Yes, sir. Now clear, sir.
Okay. It takes some time. I think there are some network. Okay, it is clear now. Okay. Here, these are the samples. I have taken A1, A0, B1, B0, A1, A0, B3, B2, right? So, there are number is A3, A2, A1, A0, B3, B2, B1, B0. These are the numbers. So I have taken A1, A0 and B1, B0 over here, and A3, A2 and B3, A2 over here, and the cross products, that is the A3, A2 and B1, B0 over here, and B3, B2 and A1, A0 over here. Now, after that, what I have to do, here A0 and B0 are
Sir,
multiplied, so this term I will get.
excuse me, sir.
Then
Excuse me,
A
sir.
crosswise multiplication, B1, A0. Hello, what is the problem? JP sir,
Sir, not clear, sir.
Not visible,
Not
sir.
visible, sir.
Not visible, sir.
JP sir.
Sir, not visible.
Now, okay, just give me 1 minute. Now,
Now clear, sir. Clear, sir. Now clear, sir.
is that clear?
Clear,
Yes, sir.
clear.
Okay. So we were over here, A1, B1, A0, B1 plus A1, B0 and A0, B0 we will get over here, right? And the same thing we will do over this term, and this term. After getting these results, these results are not forwarded over here. Carry forward is not there. So we don't have to wait it over here to compute. So we can do it in one parallel combination. So then it will be faster. Right? After this, what I have to do, I have to add it over here. Now, in the addition, we have to take care that we have to write it like this. First, A3, B3, we have to write, and then A3, B2 plus A2, B3, and then A2, B2, and then we have to shift this by 2 bits. So it is over here, and then similarly, we shift this result by two bits. So 2 bits will be here, right? And then we will add it over here, right? So we will add it over here, right? So same thing we can see through this numerical example, right? So I'm skipping this numerical example, right? Just give me one more minute. So when we implement this, right? You can see V mul2 is there, V mul2, the cross product, and LSB multiplier x1, 1x1 technique. Same thing is over here, V mul2, right? And 2-bit subtractor is there, and so on, right? So that is the part over here. Now we just give me one more minute. If you have any question till now to anyone, questions are welcome. Till now, no questions. Everyone is getting okay. Okay. Now, the problem in developing the Vedic convolution is the layout, that is the chip area, you have to optimize, right? This is the prime concern when you develop the VLSI chip. Now, another parameter which is of prime concern after the area is the power dissipation. And the third one is the delay. Area is the prime important priority-wise concern. Second is the power dissipation. And the power dissipation can be static, and dynamic power dissipation will be there. That is a different part. Third is the delay, and the delay involves the rise time, fall time, and that is the top PHL we have to find, and top PLH we have to find, right? So delay part is there, power dissipation is there, and the area is there. The fourth important part is the number of transistors, right? So we can do the optimization of the area, we can optimize the power dissipation, or we can optimize the delay, or we can optimize the number of transistors, right? Now, we have to take care, which will depend the importance of the application. Or we can navigation, we can use it, right? And there are a lot of other applications of the digital signal processing in which we can apply these trade-offs. But the point is, there are factors which you have to take care prime important as compared to other. For example, in army, we are not worried about the cost. We worry about the accuracy, because if a system we have built and if it is not accurate, then it doesn't require any meaning of arming, right? Similarly, for medical, if I see the application, in medical, there are less accurate system as compared to RV is preferable, right? And cost is not a matter. Cost can be smaller, cost can be bigger, or it depends upon the pocket of the customer or the patient which have. So there are different trade-offs we have to look for in the optimization part, right? So these are the 5 optimization parameter we have to look after it. Now we can go by reverse, right? The cost will depend upon many parameters. It will depend upon area, it will depend upon number of transistors you are using, it depends upon the technology you are using. If you are suppose having 180 nanometer technology, or you are building with 90 nanometer technology, then definitely if you are building with 90 nanometer technology, the area will be smaller as compared to 180 nanometer technology, and then it will be less costly. Developing the less number of transistor algorithms. That is, for example, if I have f equal to ab plus a dash b dash, and if I want to implement this in a CMOS topology, then in that case, this pull down network will be look like this: AB and A dash, B dash, and the network will be the dual of this. Pull-up network is of PMOS. So this will be A dash, B dash over here, and then this will be connected, and at this point we will take the output. But in CMOS, we should have a bar over here. So it is not present in the function, then we have to put 2 bars, because 2 bars will cancel out each other effects, and we will get f equal to ab plus a dash b dash, right? Now this f equal to ab plus a dash b dash 2 bars, how we can implement through the CMOS, because in CMOS this part is directly implemented over here. But for this part, we have to use another inverter. Right? So it will be look like an inverter over here. Right? So this will be V out over here. Right? Now here A dash, B dash, AB and A dash B dash is there, and here the output will be taken over here. So this is one of the technique, one of the topology we can use over here. Now, how many transistors we need? Can anybody give answer? How many transistors are there in this? Can anyone give answer? JP sir, can you give me the answer? How many transistors are there? One is Dr. MK. I don't know what is his full name. Dr. MK is there?
Yes, sir. It's Meena Kushwaha. Sir, the paper is not visible completely. Only right now, 1, 2, 3,
Okay.
eight
Okay.
transistors are in frame.
Now, Meena ma'am,
Sir, it's 10.
now, Meena Pushpa ma'am, now.
It's
Now
10.
I'm asking, it is in frame now? Not. Anybody
Sir,
can
blur
give
आ
me the
रहा है,
answer? ब्लर आ रहा है।
ब्लड सर, ब्लड आ रहा है।
2 मिनट वेट करिए, आ जाएगा। 2 मिनट वेट करिए, आ जाएगा। इट टेक्स
मतलब वो नहीं दिख रहा सही।
This design is there. Tell me the number of transistors. Anyone? Is it that visible now? Is that visible now?
No sir, no visible sir.
Not visible.
Yeah,
Just a minute.
just.
Just a minute.
Okay sir.
Now see.
Yes sir, visible sir.
Mulchan sir, is that visible?
Visible sir.
JP sir, why there is a
Yes, sir.
delay? May I ask this thing? Why there is a delay? Okay. JP sir, is that visible now?
Yes, sir. Yes.
JP sir?
Yes, sir.
Okay, JP sir, tell me how many transistors are there in this? How many transistors are there in this?
It's clear, sir. Visible.
I'm asking how many transistors are there in this? Meena ma'am, Are you getting my point? 10 is wrong. Are you getting any idea? How many transistors are there in this topology? Anyone, if can give me an answer, I will be very happy. That how many transistors are there in this design? Okay, think out. I will draw the another topology over here by which you will get this number in the meantime. Think it out, but 10 is wrong, right? Now, the second technique we can use, this is called the inverter technique. The second technique is the De Morgan's technique. I hope De Morgan's law is you know very well. Whoever is doing the CSC, EE, and EC branch, they are familiar with the De Morgan's law. I will not write it over here. I am directly using over here. So it will be F equal to, first I will open this first inverter. I will open this first inverter, right? So using the De Morgan's law. So it will be AB dash dot A dash B dash whole bar, and then whole bar will be here. This is for the second inverter, and AB dash is the first, dot A dash B dash is the second. Now in this AB, again we have to use here the De Morgan's, right? So it will be A dash plus B dash dot A dash dash means A plus B dash dash means B. So it will be this and then whole bar. Now this will be A dash into A, we have to write here. So this will be, or it will be more easier if I solve this, it will take some time, right? But more easier will be if somebody tell me what is the expression of this logic gate. Can anyone give me the logic gate name? AB plus A dash B dash. Which type of logic gate is this? AB plus A dash B dash. Can anyone give me? Meena Kushwa ma'am, AB plus A dash B dash is the symbol of, is the Boolean expression of which logic gate? Meena ma'am, am I audible to you? Meena ma'am?
Yes, sir. Yes. Yes, sir.
AB plus A dash B dash is the Boolean expression of which logic gate? Tell me fast. Meena ma'am, are you there? Meena ma'am?
XOR.
That is XOR, right? And if I take the bar of that, what will be it?
Pardon, sir?
If I take XOR bar, then it will be XNOR.
XNOR.
Right? Invert of XOR is XNOR, and XNOR expression is A B dash plus A dash B, right? So rather to solve over here, we can take this thing. The first inverter is the complement of a X OR expression, and XOR expression invert will be XNOR, and XNOR expressed into a single bar, and this single bar will be implemented by the CMOS directly, and this thing we can implement it over here. So if I implement on the same page this AB dash plus A dash B, then the pull down network, I have to do it A B dash and A dash B, and the dual of this I have to take it over here as a PMOS. Is that visible to all? Is that visible, Meena ma'am? Meena ma'am, is that visible?
Yes, sir.
Yes, sir, it is visible.
Okay. Okay. So A, B dash and A dash B is there. Okay. So that will be the output over here. That is F. Now, anyone can tell me the number of transistors in this topology as well as in this topology. How many transistors are over here in the first topology, that is the inverter topology? Can anyone? Still not. Surprising. Okay, no issue. AB, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the 10 number of transistors you are having. But this A dash and B dash are not the inputs. A is and B will be the input. You have to generate this A dash and B dash. And how we can generate? Through a inverter, we can generate A and A dash and B and B dash. And for one single inverter, this is the CMOS inverter. So 2 transistors here and 2 transistors here. So 14 number of transistors we are using in the inverter topology in this case. But in this case, these 2 will be missing. So it will be 12 transistors will be there, right? And these 12 transistors are 2 less than this inverter topology. So somebody can conclude that De Morgan's law is better than the inverter as compared to this. But that is not true. This is not the logic gate, that is the A dot B. Suppose I want to implement this in CMOS, right? F equal to A dot B. If I have to put A dot B, F equal to A dot B, in that case, first of all, I must have 2 bars, because in CMOS, a complement is necessary, right? In complement, to put a complement, we require here 2 complements because it is absent, and these 2 complements will be cancel out each other's effect. Now, if I took this into the inverter method, in the inverter method, the F equal to A dot B bar. This bar, if I put, right? So this A dot B is there, so it means this is AB term, and the dual means if it is in series, here it will be parallel. This is here A, this is B, and this is here output, right? But this is not we require. This is F bar, right? So this is not the required output. This is F bar. So how we can find out F? Simply we have to use a inverter again. And this inverter required two number of transistors, 3, 4, 5, 6. So 6 transistors are used in the inverter method, right? In De Morgan's method, F equal to A dot B bar whole bar. This we have to implement in De Morgan's. In the De Morgan's, we have to open up first this, and then we keep this. The second inverter will be implemented by CMOS. The first we have to open with De Morgan's. Is that right, Meena ma'am? Is that right, Meena ma'am? JP sir, is that right?
Yes,
JP
sir.
sir, is that right?
Yes, sir. Yes, sir.
Okay, okay. Now, if I build this with the CMOS, A bar plus B bar, here it is A bar, here it is B bar. This plus indicates parallel here in the pull down network. So that's why we have to put it over here. And A dot B, this dual of this will be over here. So it is the series connection, we have to put it over here. Now here, the part is like this. Here this will be the output. So this is here A dash, B dash. Now can anybody tell me fast how many transistors are there? Fast. Participant, hurry up.
4.
Wrong. Meena ma'am, again wrong.
Okay, 2 more. 6.
Anyone?
2 more, sir. 6.
No, again wrong.
We need 2 transistors to complement A and
Anyone?
B.
Just a minute, just a minute. Anyone else? Anyone else? How many transistors are needed in this? Oh, come on. For A dash, we need 2. For B dash, we need 2. So 2 plus 2, 4, 5, 6, 7, 8. These are the 8 number of transistors we need. Right? Here it is 6, here it is 8. In this case, De Morgan's is not better. Inverter is better. Inverter method is better. In the previous case, the inverter method was better. Sorry, De Morgan's was the better. Yes, this slide. You can see here in De Morgan's 12 and here 14. So it does not depend. It is not true that De Morgan's is better. It is not true that inverter is better, right? In some expression, inverter gives the less number of transistor topology of the CMOS. In some other expression, De Morgan's is better than the inverter. So you have to take care of this design. So whenever we design any system, the prime concern is the area, and area will be decided by the number of transistors you are using, as well as the technology we are using, right? Now, we can have 5 minutes break, and after that we will again start the things. Or rather 10 minutes break we can have. It's 2:15, we will again start it, right, from this point. Because this session is up to 4 o'clock, so definitely some freshness is required. So we will again start it at 2:15, right?
Okay, sir. Thank you, sir. Thank you. Thank you all of the participants. After we will meet at 2:15. Thank you.
Oh, very good. Very good afternoon to all of you. Am I audible? Preeti ma'am is there. Preeti ma'am. Preeti ma'am, am I audible to you? Kamlik Dixit sir, am I audible to you? Preeti Sengal ma'am, am I audible to you? Ram Saini sir, am I audible to you? Ravi Teli sir, am I audible to you? Vijendra Maurya sir, am I audible to you? Dr. Virendra is there? Dr. Virendra Maurya? Dr. Vijendra Maurya? Jitendra Yadav sir?
Yes, sir.
Am I audible?
Yes, sir.
Audible, sir.
So, coordinator, can we start?
Yes, sir. We can start, sir.
How many active participants are there?
Approximately
Coordinator, how many?
10 participants at present time, but they are not available to listen, sir.
But I am asking active
Okay.
participants. Preeti ma'am is there? Bhushan sir, please ask whether all are available or not. Then we can start.
No.
Bhushan sir?
Hello. 15 is
Bhushan sir, please ask.
15.
Please
15.
ask to the participant.
Okay, sir. Hello. Please participant. Hello.
Yes.
Can you listen to me?
Yes, sir.
Okay, sir. We are starting the session. Hello.
Okay, sir. Start.
Okay, sir. Doctor Sir.
Yes.
Hello, sir. Sir,
I'm here.
we can start, sir.
Okay, okay. Just I'm connecting with my laptop. Give me 2 minutes more. Dr. Sabir is there? Okay. Hello. Uh, Hello. Am I audible to all?
Yes, sir. Audible, sir.
Okay. And video is also, the paper is also visible.
Yes, visible.
Okay. And the writing is also visible. Writing is also visible, Mulchan sir.
Yes, sir. Visible, sir.
Okay.
Visible, sir.
Now, there is actually there is a problem in laptop. The file which I want to show you the participant, there is a problem in that, but there is no. I have a B plan for this this problem to eradicate. That's why I'm taking so much of time. I had opened twice or thrice time, but it is not opening due to some errors. It is showing that particular design is not opening in this particular laptop of some of the faculty I have taken. So no problem. We were at the point that we are having a transistor topology, that is we can use the inverter or we can use the De Morgan's law. Now, in some method, the inverter topology is better as in terms of number of transistors required, less number of transistors required. And a VLSI engineer main task is to reduce the number of transistors. And also, we have to optimize the using the technology node. Nowadays, 16 nanometer technology is used. Is this visible? Mulchan sir?
Yes, sir.
Okay, is that visible?
Yes, sir. Visible, sir.
Okay. So 16 nanometer technology node is there, which we use. We have to use the 16.5 nanometer as the channel length. So 16.5 nanometer technology channel length will be there in the technology node 16 nanometer, which is nowadays we are using, but more in near about 10 years, it may be reduced to 2 nanometer. That is in 2000 around 24 or maybe 25, the designer can design their technology using the 2 nanometer, and you can understand if we design with the less channel length of the transistor transistor size get reduced, and at the same time problem That problem is the sub-threshold problem. Sub-threshold is the process or the sub-threshold current, rather we can say it, whenever there is a channel length is smaller between the source and drain, then there will be a problem of body biasing and other second order effects will be taken care. So how to remove these subthreshold effects? For that, there are a lot of research going on, and they require if you require, you can go to the Google Scholar, and in Google Scholar there are a lot of research papers are available. You can read these and then you can build your own research and the idea can come. Here, if the channel length is smaller, then apart from the subthreshold, there are a lot of other things will come. That is, the second order effects will come. The channel length modulation, body biasing, and there are a lot of other effects will come. We have to remove those effects. We have to look after those effects, right? And in Vedic convolution, which is the topic of this session, we can use the advanced adders, we can use the advanced multipliers, and we can use the other advanced uh, subtractor and divider and so on. But here, what I mean to word advanced means the latest adder or the latest multiplier, which is the researchers have found out. For example, the XOR gate we can build with the nowadays with the 3 transistors instead of 5 transistors or the 8 transistors. We can build with the 3 transistors only. Right? So researchers have developed that 3 transistor topology is there of the XOR gate. You can search it through the Google Scholar and you can find out those things. Now, the Vedic convolution, in this, the multiplier which we have to implement to understand, to implement the Vedic convolution, in that also there are a lot of research are going on. I have used the Nikhilam multiplier as well as the Anurupen multiplier as well as the Urdhva multiplier to build this Vedic convolution approach. And my approach I have shown you on the previous session. And I hope everybody is having the understood of my research. There are 2 methods. One is the back-end approach. Another is the front-end approach, right? Can anyone give me the answer of this? So what is the back-end and the front-end? Anyone have the idea of that? Can anyone have an idea of that? Back-end design and the front-end design? Can anyone have an idea? Please say at least no or yes so that I can not wait. Preeti ma'am, are you there? Actually, this is the faculty development program. So if you are not instructing, then it is not fruitful for you.
It's right, sir. Mostly faculty
Dr. Vijendra is there.
should be give the answer, sir.
Dr. Vijendra sir is there. Ravi Teli is there. Ravi Teli sir, आप हैं वहां पर?
Please, participant, speak, please.
Yes, sir. Oh, who is speaking? May I know your name, please?
Yes, sir.
What? Yes, sir. I am asking
Please,
the name.
please, participant, speak, sir.
Speak with your name, please.
Here, Preeti Senga, Ram Saini, Rampal Prajapat, Ravi Teli, Shailendra Sharma, Tina Bhati, Vijendra Maurya.
Yes, sir.
Yes, sir. Tina. Yes, sir. Vijay Maurya here.
Yes, sir.
Okay, Dr. Vijendra, I think
Yes, sir.
you know the back-end design and the front-end design. Can you give me that so that it will give me?
Sir, backend design totally based on the software. Like Cadence company, Synopsys company, and Viraj Logic are doing their work on the backend. Front end totally based on manufacturing, like doping, metallization, oxidation. These are based on front end. मीन्स टोटल मैन्युफैक्चरिंग जो हार्डवेयर होती है वो जो है होती है फ्रंट एंड पे, और जितनी भी डिजाइन होती है सॉफ्टवेयर पे जो आप सिखा रहे थे कल, जो है टेनर डिजाइन करना, इन्वर्टर डिजाइन करना, सब टोटली सब बैक एंड है.
Okay, okay. So which one come first?
सर बैक एंड एंड आफ्टर दैट फ्रंट एंड. पहले सर डिजाइन होगा देन. नो सर बैक एंड फर्स्ट.
No, sir. No, sir.
सर बैकएंड से ही टेप आउट होके फ्रंट एंड में जाता है.
एक मिनट में एक एग्जांपल बता सकता हूँ. जब भी अपन बैडमिंटन खेलते हैं तो बैकएंड पहले सीखते हैं कि फॉरएंड पहले सीखते हैं?
नहीं सर, ये मैं बता रहा हूँ प्रोसेस का, सीखने के बाद में प्रोसेस का जो.
I'm asking one question.
हाँ.
Single the question. I'm asking this question. When we try to play badminton, the badminton player can learn the backend first or the forehand first?
Sir, both are different thing. The backend engineer and front end have no relation, sir. Only tape out process.
Sir, I will prove this. Give me 2 minutes or 3 minutes time.
Sir, मैं इसी में काम किया हूँ सर, वो तो. सर फ्रंट एंड में सर मैंने 8 साल काम किया इसी में, पता ना वो जो बैकएंड आता उसी को आगे हाँ मैन्युफैक्चरिंग करते हैं. हाँ
सर can you give me the VLSI design flow? Can you show
सर कैसे? नो सर, not right now. कैमरा
VLSI design flow?
हाँ.
To the paper you can show it.
सर
In VLSI design flow, first the back end is coming or front end is coming?
सर फर्स्ट भी बैक एंड कमिंग सर. आप मेरे पास है, मैं अभी.
No, absolutely wrong. Absolutely wrong. Absolutely wrong. In VLSI design flow, we have the specification.
हाँ, system specification, yes sir.
After the system specification, we have the logic gate implementation. Sir, please, let me complete. I have given you the time, right? You have not speak out at that particular moment. Now it's my turn. specification and then logic gate. Rampal ji, somebody mic.
सर मेरा डीजल खराब हो गया। अरे बोल दिए पेट्रोल डलता है बाइक में, तो डीजल की कौन सी बाइक ले आया तू?
Rampal ji, your mic is on, still on. Okay. Specification, after this specification, the logic implementation will be there through the logic gates. After the logic gates implementation, there will be a circuit implementation, circuit level. After the circuit level implementation, there will be a layout level implementation. And after the layout level implementation, there will be a chip fabrication. That is, this layout will be given to the foundry where the chip is manufactured. In this logic implementation, we do using the Boolean expression, and in that Boolean expression, we use the logic gates, and that part is done, up to this part is done by VHDL or Verilog or System C. These all are HDL, that is the hardware description languages, and this part is known as the front end, and this is done in Xilinx software. And from the circuit level implementation to this layout level implementation, this is done in the Tanner EDA tool, which I'm using, or Cadence is also there, Mentor Graphics is there, and there are a lot of other tools, graphical tools are available. The layout and this is called the back-end design. And now why I'm saying this back-end design comes after the front-end design, because it is very crucial. If we suppose build reverse, suppose we build layout first, right? And suppose chip we find out we manufacture the a foundry can build. Foundry can build. Cost of the foundry is very large. So that's why we cannot put a faulty layout over here station, and then it goes to the circuit level, and then to the layout level, and then the chip foundry will be there. So first we have to check it in the software, and this software languages VHDL, Verilog, or System C. In these languages, it is easy to change the program, and then that can be burned on the FPGA to check it out whether my design is right or wrong. If it is right, then we can proceed to the next level, that is the circuit level or the layout level. And after satisfying that circuit level is right, after that we can go to the layout level, and then we can go to, and then there is no use to put the logic gate after the layout level design. So this backend design will come after the front end design. Dr. Vijayendra, are you agree with this?
Yes, sir.
So participant, please don't mind this conversation, but it is a healthy conversation. It should be in, we should know the correct things. Backend design comes after the front end design, and it is a common example. That's why I correlate this with the badminton. First, whenever we play, हम सीधे हाथ से खेलना सीखते हैं, फिर उल्टे हाथ से हमें सिखाया जाता है, क्योंकि जब सीधा सही से आ जाएगा तब तो उल्टे हाथ से आएगा ना. So that is the correlation example. That's why I put it over there. Now we come back to the Vedic convolution part. We were discussing this Vedic in this Vedic convolution, the advanced adders and multipliers also going on. This adders, there are CAG stand adder are there. There are lot of others are there. CLA was there. Carry look at adder, carry save adder. There are many adders are there, right? So there are a lot of research going on. Multiplier, as far as concerned, the Vedic multipliers are giving better results as compared to Booth multiplier, as well as the Wallace multiplier, which are the Booth and Wallace has generated. But this Vedic multiplier is better nowadays. Our foreign researchers are looking after this Vedic multipliers, and they are doing their chip fabrication on this Vedic multiplication, right? So that is about the part, the research part, which anyone of you who is doing. I know there are doctors are there, but they can do the postdoc, and then the multiplier is still they can design in their postdoc. It does not matter that the multiplier is a simple thing, so what the research can be there, but I can give you in multiplier that I have designed in the CMOS as well as in the multi-channel CMOS. So multi-channel CMOS and CMOS. Right? This is here. Is that visible to all? Dr. Vijay, is that visible?
Yes, sir. Visible. Yes, sir. Visible.
So,
Yes, sir. Visible. Visible.
okay. So, in the complementary metal oxide semiconductor, is the topology in which all the channel length of all transistors are same. But in multi-channel CMOS, which is in short called NCCMOS, in this, the channel length is not same, right? So what is the use of the channel length same, and what is the benefit of the channel length not same? As far as the manufacturing is concerned, we require the uniformity in manufacturing. That is, the foundry person who is designing the chip, they require a design which is having a uniformity. That is, they prefer the NMOS topology as compared to CMOS topology. That is, all transistors are with the NMOSs. We can also design with the PMOS also, right? PMOS topology is also there. But drawback of the NMOS and PMOS is that we cannot get the full swing VDD. Full swing of the NMOS and PMOS topology, and that's why we are using the CMOS topology. But the CMOS topology is having a problem that when we give the inputs to the CMOS, it will provide the output after certain time, that is called the delay time. Now, in this, the channel length is same of all the transistor, whether it is NMOS and PMOS, and this channel length will be the technology length. What I mean that suppose if I'm using 0.5 micrometer technology, which is very, very older, 2004, we were over here at 0.5 micrometer technology, and nowadays we are using 16 nanometer technology in 2021. But there are technology nodes are available, which is available in the Google. If you type it, technology node, then you will get the standard is 16 nanometer in 2014, and after that there are a lot of other nodes are available. You can search it through the Google and you can find it. Now, in this 16 nanometer, the channel length L is not 16, it is 16.5 nanometer. Can anyone give the answer why we are using more here? Participant, can anybody give me answer that why we are using 0.5 more as a channel length if we are using a 16 nanometer technology node? Dr. Vijayendra?
No, sir.
Meena ma'am?
No, sir.
Ravi sir?
Mic off.
Ravi sir?
Ravi sir is not here, sir.
Okay, okay. Mohammed Sabir is there? Sabir sir? Sabir sir? Mohammed Sabir sir? Bhulchan sir, Mohammed Sabir sir हैं?
No, sir.
Okay, okay, okay. Can anybody give answer to this question? Why we are using 0.5 more as we are using? We should use 16 nanometer. Why we are using 0.5 more? Actually, this should I give the answer, participant, or anyone want to try? Dr. Vijayan? Dr. Vijayan?
Yes, sir. Hello.
Should I give the answer? Should I give the answer?
हाँ सर दीजिए ना सर.
Okay, okay. So, actually, there is a phenomena which is known as lateral diffusion. So, lateral diffusion is what? Lateral diffusion, this is my N plus, this is another N plus, this is your source, this is your drain, this is your polysilicon. Before that, there should be SiO2. Here, there is a polysilicon. Right? This is the structure of a MOS. Right? And this is the here there will be a body will be there of P plus, P-type body will be there. Right? So if there is a P-type body, there will be a N channel here. So it is NMOS. So here, this N channel will be enhanced, and that's why it is known as enhanced mode NMOS. Now, why we are using here more than 0.5? Because when we build this N plus using the fabrication approach, then that approach we are using as ion implantation. And ion implantation method is that we bombard the N plus ion over here. That is the phosphorus ions we bombard over here in this direction. And when we bombard over here in this direction, initially they will reach over here and there will be a transversal diffusion will be there. That is, the transversal diffusion is the diffusion in the direction of the force. And after some time, there will be a lateral diffusion will take place. That is, this ion will move in this direction. That is, to correlate this thing, I am giving one example. Suppose we have a jar and initially we put a balls in this direction. So initially what will happen? They will come over here, right? Initially they will come over here, right? After some point, if a point is if a ion is over, if a ball is over here and some other ball is moving, it will hit this ball and this ball will move in this direction. That is called the lateral diffusion. And due to this lateral diffusion, we will not get the same alignment of this boundary of drain and source as we have the boundary of the gate and SiO2 layer. That means, that is what I mean to say, that here I want this, but it will become like this. That is, there is a lateral diffusion will take place in this. And due to this, this is the actual length, which is 16 nanometer. But this is the portion which we create in the schematic editor, because in schematic editor or the channel length in which we are choosing is not giving the actual length, because we cannot decide this 16 nanometer, because that is decided by the foundry person, that how many ions they are throwing. They will decide by themselves, right? So as a schematic editor or as a layout engineer, we have to take care of this length. That is called the gate length, right? And this length is the channel length, which is the technology length. Are you getting me, everybody? Dr. Vijay sir, are you getting my point?
Yes, sir. Yes, sir. Getting. I am getting.
Any confusion in this? Why we are getting this more than
No, sir.
0.5
Clear.
over here? Okay. Thank you. So we were over here that we are using this MCC-MOS, the channel not same, and in CMOS channel length is same. If the channel length is same in CMOS, then there are some drawbacks of it. That is, whenever body bias should be chosen, and that critical length chosen will be decided by the VOL level. VOL level is the logic low level when the output is in low or input is in high. So when we get the VOL level, then there should be a critical path of the transistor we have to use, and in that critical path, the channel length we are using should be optimum. It should not be same. Why? Because channel length will decide the subthreshold current. The subthreshold current, that is, it will be if you have the idea that ID is proportional to W by L, then if channel length is smaller than the other transistor, the current will be higher. So if I want to reduce the subthreshold current, then ID if I want to reduce the subthreshold current, what I have to do? I have to use the lower channel length. Is that right? Dr. Vijay, is that right? Dr. Vijay, Meena,
Yes, sir. Yes, sir. Right, right.
ma'am. Okay. So when the uh, ID is higher, we require the channel length smaller, right? So in some transistors, we require less current, and in some other transistor, we require the higher current. How it will be decided? It will be decided by the application. In some application, requirement is higher, some other application current requirement is smaller, and that's why in some transistors we have to change the channel length and keep the other transistor channel length same as the technology length. That is, there will be definitely a lateral diffusion included, but all transistors are not manufactured with the same length in the MCCMOS, and the reason behind it is the subthreshold leakage current will be reduced in the MCCMOS, right? So that is the advantage of MCCMOS, and that's why nowadays the CMOS is obsolete. We can go to the MCCMOS and other higher CMOS versions we can go. So in the MCCMOS topology, there are a lot of other benefits are there. You can Google it and you can find it out, those things. And if you not get that thing, you can contact me. I can provide you the things in a easy manner. Now after that, in Vedic convolution, we can use the MCCMOS topology. We can use the number of transistor less, that is the De Morgan's or the inverter method, to do the more research on that, and we can develop the more research area. Right? I have I have done with that Vedic convolution approach. If anyone have any problem, we can have a discussion, healthy discussion. We can have separately. I can provide you my number, my WhatsApp number. Every I think known to you. But if it is not known, this is my WhatsApp number. You just WhatsApp me. I try to solve your DSP and VLSI related problem. So, and my email ID is suharsh.rajesh@gmail.com. So if anyone wants anything, I can provide that thing. And from that point, from my side, it is over. If participants have any query on my lecture, so it's over to Mulchan sir.
Yes, sir. Hello.
Mulchan sir, I have done.
Okay, sir. Okay, sir.
So if participant have anything, or we can close this session.
Please, if you want to ask some things, you can ask to the sir. If the session is finished. Anyone interested? Hello. Okay, sir.
Okay. Thank
Okay.
you very much to all of you. It's
Okay, thank you, sir.
wonderful
Thank you.
to. Okay, it's wonderful to talk to give my research area to all of you. Hope everybody will have some idea of that and they can have benefit of it and they can give their research paper. And again, I'm saying if you find any difficulty in that research paper, we can discuss it anytime. Right? So thank you very much to all of you. Have a good day to all of you.
Thank you, sir. Thank you.
Thank you for all the participants to attend the full day FDP on MATLAB and VLSI optimization. The session is very fruitful to all. Now we again to come on the validation programs. Please cooperate us.
Can you send feedback link, sir?
Yes, sir. Sir, our validation program is starts 4 to 4:30.
Okay, sir.
Okay, sir. Thank you, sir.